Let's move on to forests as carbon sinks and sources. This is a share of land covered by forest from FAO. Obviously, a definition is needed. I think it's any 5 square kilometer area that is covered by vegetation. Obviously, you can see the ranges here, and it does a good job in terms of capturing the thicker coverage of the Amazonia, Central African forests, and some of the temperate forests up here, tropical rainforests down here as well, and so on, and shows the range of coverage from 20 to 30% down to even 10%, and the deserts as well as the lush coverage of the thick forests. There are many maps you will find which show the biomes, which get very complicated, and many categories of biomes. In general, forests are broadly classified as tropical, these green colors here. Temperate forests appear in the mid latitudes, and boreal forests at high latitudes, and there is tundra if you go into the Arctic Circle as well, which is not shown here. So obviously this also kind of captures the climate regimes, temperatures, humidities, precipitation, etc. And the seasonality of these forests changes with climate, as well as the composition of trees and their character. Just to take a look at the estimated sources and sinks of carbon, I took this figure from this paper in Science, showing these histograms. When they are pointing downward like this, they are sinks, and when they're pointing up like this, for example here and here, they are sources. Okay, so light and dark purple, globally established forests. So you have boreal, temperate, and intact tropical forests being shown here. So you can see the color scale here. Tropical forests in Asia, Africa, and the Americas. Temperate forests all over the place here. And you can see the main message I would leave is that if you look at petagrams carbon per year as a flux. Okay, this is not gigatons. Here listed as petagrams, which is just the same as gigatons per year. So it's a stock, not a flux. Sorry. You can see that there is a sink here, sink and source, sinks, and various biomes or forest types. So the main message is that the forests are still considered a persistent sink of carbon, but we know that there are always wildfires up here in California, parts of Canada. Australia had a mega wildfire that killed like 1 billion animals, which is fairly sad. So if you look on the other hand at deforestation, going all the way back to large colonizations of various continents by people, you can see that the temperate forests were being cleared. This is deforestation in million hectares. So the temperate forest deforestation has dropped off, whereas the tropical deforestation increased and peaked in the 50s to the late 70s, and then has dropped off, especially potentially related to the awareness and agreements under Kyoto and Paris about reducing emissions from deforestation and forest degradation. But if you look at the amount of emissions resulting from deforestation, this is figure from the World Resource Institute that says if tropical deforestation were a country, it would rank third in CO2 equivalent emissions. So there is China, about 12 gigaton CO2 equivalent per year. US is the next, and tropical tree cover loss would be the third country in this list. So this is the argument about planting trees, that unless the trees are left protected from deforestation and perturbation, you will end up creating a lot of losses. Plus, if it is a zero-sum game where the resources for mitigation and adaptation are going to go either into planting 1 trillion trees or doing something else, then we have to be very careful about the exact role of forests in mitigating climate or bending the curve, especially since the agreement and land required to plant 1 trillion trees and the ability to not introduce invasive species and so on also become critical. Okay, that'll probably be debated for a while in terms of planting 1 trillion trees, and that should not be also seen as a silver bullet. If people say we are planting 1 trillion trees so we don't need to worry about reducing emissions, then obviously we haven't really solved the complete problem. The broader perspective on this is also important. If you look at our Mauna Loa time series, which is up here, and the variations of atmospheric CO2 concentrations estimated from the beginning of the Holocene using ice core data before 1958. This goes up to January of 2018, so we're still now we are at 420 or so in 2020. But carefully analyzing these actually shows that there are blips here that correspond to people abandoning land, agricultural land, and regrowth of forestation. For example, after large number of deaths during the Black Plague or the Spanish flu and so on and so forth. So all kinds of information is hidden in there. So this is the atmospheric CO2, but one can also look at estimates based on data and some models about the soil organic carbon relative to 10,000 BC. Here, going beyond the zero common era, it's considered no land use change. So the SOC loss is shown here. Used land in million square kilometer is shown here. So grazing land, cumulative SOC loss in petagram carbon, and croplands and the SOC loss. So you can say that human impact on soil degradation and carbon loss has been going on for several millennia at least. Okay, so agricultural way of land has always been a total negative impact on soil quality and soil organic carbon, and added to atmospheric CO2 increase. Industrial revolution and population growth in the 20th century obviously kicked everything into high gear, and super exponential growth of CO2, deforestation, population, food demand, agriculture, soil degradation, and so on.